This is a typical bellows that we talked about, measuring pressure. You can see how it works. This hole right here is where you mount it at, so you mount it against something solid that don't move. And then of course you put your pressure here, and depending on the pressure would determine how much it expands, or in a vacuum you could actually use it to measure a vacuum too, right? Because when you put a vacuum on it, then what would it do? It would compress, right? You understand that? And then of course when we put a pressure on it, it would expand. So this is one of our typical pressure sensor. Of course, pressure, usually when we talk about pressure, we talk about positive pressure, and then negative pressure we call some type of vacuum. All right? Everybody okay? Let's see this. Chords. I wish you wouldn't listen to music while I'm up here talking, or whatever you're listening to. Of course, we don't have class Tuesday, right? And Thursday, we have a test. So is anything y'all need to go back over? What do we need? What do we need to do? I mean, what do we need to go, anything we need to go back over? Now, of course, y'all understand that when I give you these labs out, there's a big section called discussion in there, right? You understand? And y'all realize anything in that discussion can be over a test. It's your responsibility to read those. Everybody understand that? So there's some things on there that we talk about in lecture that they cover a little different. Like a through the beam, I think people refer to it as a direct scan. Yeah, but it's still the same thing. It's just terminology. But you know the difference because hopefully you've been reading those discussion sections. And of course, that's why I give those out separate so you can do what? You can take those home and read them. Some of the things y'all need to make sure you understand, of course, is we're dealing with a lot of solid state sensors now. And of course, like I said, we probably need to set up a lab. I need to put that in my notes to add a lab on a limit switch because that's not solid state. That's actually an electromechanical device. Right? In solid state, we picked up some terms. We picked up operating current. And then we picked up load current. And y'all been measuring these. Leakage current. Yeah, usually. And then holding current. Of course, you haven't measured holding current because it would be hard for us to do that. So what's operating current? Well, not operating current. Current is the current required to make it operate. Okay, you understand? Load current is what's flowing through the switch when it is activated a load, right? You understand? But what's the holding current?
Is it anything like holding force?
Well, on relays, we have what we call a pull-in voltage, and we have a holding voltage. So on relays, the pull-in voltage or the pull-in current is a lot higher than the holding or the holding currents because it's got to pull that relay through that gap. Well, when these things switch, these solid state devices that they switch with, if you don't maintain a certain current flow through them, then they'll switch off. So that current the minimum current that's required to keep that solid state device on once you turn it on is called a what? Holding current. Y'all understand that? So in relays we have that too. So that means if I it takes a voltage that pulls it in. If I don't maintain the minimum voltage, then what will it do? It'll drop out. Okay, understand? But on this, it's a little different in that most of your solid state devices, especially devices called SCRs and triacs and stuff like that, those suckers have a holding current, which means if your load does not pull enough current, the thing will turn on, but then it will do what instantly? It'll turn off. So that makes sense. So in AC, we use two devices. The primary device we use in AC is a device called a triac. And all our sensors are solid state sensors. And the way a triac works is that if you put AC on it, a very small AC, then it'll pass a big AC. So it acts like an AC switch, but it's controlled. But to keep these guys on, you have to maintain a certain current flow to those once you do what? Once you turn them on. Now, some of your sensors literally have, some of your sensors use magnetic reed switches. And what's nice about those sensors is that they can control DC or AC. So an AC sensor can only control AC. A DC sensor is either going to use a NPN transistor or a PNP transistor. An NPN transistor we use as a sinking, right? We talked about this in this class. And then a PNP is primarily used for sourcing. And it depends on what you're looking for. If you're working with PLCs, a programmable logic controller, your input is either going to be a sinking input or a sourcing input. So if your inputs are sinking, then your sensors have got to be what? Yeah, to get current flow, you have to have a source, and then you have to have a common. Of course, in DC, it could be either way, right? You understand? Normally, so that means if I'm gonna make current flow, if my common, if we use the negative, we refer to this as sinking. If we come over here and use the positive, we refer to this as sourcing. You got to make current flow through that thing. So if your PLC provides the negative, then your sensor's got to provide the positive. So in PLCs, plus is sourcing and what? Minus is sinking. If your PLC provides the source, then your sensor's got to provide the minus, right? You understand? So that means if you have a sourcing input, then your inputs devices have to be what? Sinking. Y'all understand that? So normally this will be specified in the PLC. Now, Allen Bradley PLCs, depending on how many inputs they have, they're modular PLCs. When you buy an input module, you specify is it being what? Sinking or sourcing. When you get their fixed PLCs, normally they're fixed PLCs, they'll divide the input up into, in fact, I'll show you. So this is a small 1100 PLC, which is pretty cool. but when we come and look at the inputs and the outputs, so this guy's got relay outputs, which what's the advantage of relay outputs on the PLC? What's the advantage of a relay output on the PLC? Well, you can put AC on, your outputs could be AC, they can be DC, they can be sync, or they can be source. It depends on. Yeah, so when we look at the inputs, so they get it. We get it. If you look at the outputs, every output has a common, and they've got either DC or AC, DC, AC, DC, AC. So what that means is that I would have to hook up a common for every output, but it's up to me to decide whether I'm going to hook it up syncing or sourcing, or whether I'm going to hook it up to AC. And when we look at the inputs, if it'll focus in, this group of inputs has a DC common. This group of inputs has a DC common. What does that mean? Well, what's the common? What could the common be? It could be positive or it could be negative. So it's up to you to decide if you're going to hook these up syncing or sourcing. But it's not unlike the inputs. Unlike the outputs, you choose each output, right? You understand on this because it's got relay outputs. On this one, you have a group. So we input 0 through 3 has its own common, and then inputs 4 through 9 has its own common. But a common is not necessarily, it's just what you consider to be common for that circuit, right? You understand? So if you hook up the positive on these, then that would be sourcing. If you hook up the negative up here, then that would be what? That would be syncing. So it's up to you how you hook that up, which is pretty neat. This guy here's got 2 analog inputs. So this is where we can hook an analog sensor up. And I don't know what it gives, but I'd have to go look. The little Arduino gives you a number between, it converts it over to a number between 0 and 1023. And then it's up to you to scale that, right? That makes sense. So it's up to you to scale that with your PLC program to say, okay, you know, this number would equal this speed. Does that make sense? Yes or no? I did learn how to scale with the Arduino. The Arduino, its analog inputs is 0 to 1024, but its analog out, its pulse width modulation is from 0 to 255. So you have to scale. So you're defining this range equals over here equals this range. So, like I said, so you only deal with syncing and sourcing when you're dealing with DC, right? Understand? AC basically has no polarity. Don't understand that. So even Alabama Power, the thing is changing polarities every 8.3333 milliseconds. It's swaps polarity. So you okay on syncing and sourcing? So our sensors, our DC sensors are either going to be what? Syncing or sourcing or relay. Now, if they got relay outputs, then it's up to you to decide whether it syncs or whether it sources. But what's nice about a relay output is it can also run AC. So it's real nice about the PLCs. The disadvantage of relay outputs is what's the disadvantage of relays over solid state devices? Well, one of them is this. One of them is this. And then the other one is this. The failing. So relays have two capabilities of failing. They can fail mechanically or they can fail electrically. Solid state devices can only fail what? Electrically. There's no mechanics in there. That makes them reliable, or more reliable than, yeah. So that's your biggest disadvantage. Plus, usually electronics is faster than mechanics. So that's another real advantage. Any questions on strain gauges? So what do we use strain gauges for? Actually brought one in. I got one up here somewhere. Huh? So we use a strain gauge. So what a strain gauge is we come over here, and I could bring the picture back up, but all it is wire.
Oh wait, it's stretch out a wire along for a small circle.
Now, yeah, what determines the resistance of a wire? Yeah, the length, the size. Got four things: material. Got one more. Got temperature.
Yeah.
So a strain gauge is going to be made out of a certain material. So y'all understand that. So I don't control what the wire is made out of. Okay. Well, after I buy it, the manufacturer determines. The manufacturer determines what we got, right?
Yeah.
I don't know where. Usually I carry a rubber band around because it's a perfect example of how a strain gauge works. So when we come over here and push on this thing perpendicular, what's that going to do to the wire? Well, what happens to a rubber band when I grab it and pull it out like this? It gets longer, so I've changed the what? And I've changed the size. Right, you understand? What happens when I come up here and push the band together? It gets smaller and it gets fatter. That's a strain gauge. So if I stretch it out, if my weight stretches it out or my force stretches it out, the resistance is going to go up. If push it together, the resistance is going to go down. Okay, does that make sense?
Or
bigger path. And these guys are extremely accurate. The only thing we got to do is compensate for our temperature. So we always to get an extremely accurate rating, we need to mount these things. We need to always go in pairs, or we need to go in pairs. You can make it work, but without a second strain gauge, but now it's going to vary with temperature, right? You understand?
Yeah.
Yes or no? So what we do is we run these things perpendicular to each other. So one of them acts like an accordion, the other one acts like a gauge. So if I got an accordion, y'all understand what I'm saying? It's not going to change with weight, but it's going to change with temperature, right? You understand that? So we got one that we put perpendicular, we got one that, so they're always, they should be mounted like this to be extremely accurate. And then of course, we bring that into a bridge. We call this a Wheatstone bridge, right? Normally, they'll draw it like this. But this is not hard. This is pretty hard to draw. So normally this is the Wheatstone Bridge, and what we do is we put a voltage across it, and then this is where we would take our output right here. I hit erase all. Well, this is a true erase. That's not a cut and paste. Yeah, see down here you got this thing that says erase. So what we do is we take our output across here, and then this would run into what we refer to as a differential amplifier. So if we come up here and it really concerns me about people don't understand a difference in potential. Because if I come over here and let's say this is 1K, this is 1K, this is 1K, this is 1K, and I come up here and put 10 volts right there, then what would we have right here if I use this as my common? What would we have across this resistor right here? And we have 5 ohms. What would I have across this resistor right here? And if I came over here and put my voltmeter across that, what would it measure? A difference in potential. So what I would have is I have plus 5, a difference, a minus plus 5. What would I have? So 5 minus 5 is 10.
You got 0.
Okay, you get 0. A difference in potential. So anytime we say difference, we're talking about subtracting. And that'll get people confused too. So, you know, I'll come up here and I'll put a battery pointing this way, right? You understand? And I put a battery pointing this way, or like we did, yeah. So these in series. Well, over here, this would be if I come over here and measure this. This might be a plus 10 volts. I come over here minus this. This would be a minus 10 volts. What would be my difference in potential? 20 volts, right? Because it's a watt. It's a difference in potential. It's just like we were doing the power supplies last night. You wasn't here, Larry. But we were hooking power supplies in series. And yeah. Well, it smoked. I mean, it was hooked up right. I don't know what's going on with it, but
Yeah, I don't know.
things happen. But see, I would come over here and I'd say plus 10 minus a minus 10. And what is, if I, in sign math, a minus 10, what does it tell us to do? Change the sign and add, so that means we'll have a difference in potential of 20 volts. And this works for batteries, it works for power supplies, even electronic power supplies, right?
Yeah.
So if this, so we would call this a balanced bridge. Y'all understand that? It's called balanced. If it's unbalanced, then let's say this right here goes to 2K. Well, this over here is still 5 volts, right? You understand? What would the voltage be over here now? It's going to be 1/3, which would be what? Huh? It's going to be 3.333, right? Volts, right? No, I'm sorry. It's going to be 6.6. This is the big one down here. It's going to be 6.67 volts. This is gone. The bottom is going to drop 2/3 because it's 2/3, right? 6.67. So what would my meter measure now?
negative 1.4.
Well, yes and no. It depends on what you use as the reference, right? You understand? Yes or no? So if I put my black lead on my meter right here, and I put my red lead on my meter right there, then it's gonna measure a plus 1.67 volts. If I call this my negative and if I call this my negative and this positive, then it's gonna measure 1.67 volts. So the bridge, what you get out of it, depends on what you use as a reference, right? Understand what I'm saying? So what they do, of course, is they come over here and one of these will be what we call the active gauge, and then the other one will be the compensating gauge. So that means now this guy takes care of what? This guy takes care of temperature. And if this guy changes, then we get an output relative to weight. Y'all understand that? So this is why if we're going to get an accurate reading out of strain gauges, we always use these things in what? Pairs. And we run them through a Wheatstone bridge. So we have a thing called a load cell. So we buy load cells. Yeah, they're cool. So this is a typical load cell. So your strain gauges are mounted on whatever you want to measure the force on. And then that would be here, right? You understand? So they're doing it like this, but notice they're exciting in the center. It's still the same thing that we do. And then they take the output off right here. And this would go into your scale. Into your indicator. One of them's in there, we call it the active gauge, the other one we call it the compensating gauge. What's the compensating gauge for? You might know what you're talking about, but that wouldn't be the way a question was worded. So that's in there for this. Yeah, it compensates for temperature. So they're mounted right next to each other. So that means if this one's at 100 degrees and the other one's at 100 degrees, they're both got the same leaf. They're both got the exact same gauge. They're both got the same length. So one of them's resistance goes up. Well, this resistance would go up, but they would go up exactly the same, right? You understand? So their resistance would change exactly the same. So now if my active gauge changes, it's not because of temperature, it's because of weight or force. Okay? Y'all understand that? We don't have any load cells. They're not cheap. Don't know where we got a load cell. I used to work for a scale company. Knowing I was going to teach this back then, I got a load cell from especially what we call split beam. So they got different ways. You can run them in compression, or you can run them in, or you can actually put it on a bar and actually bend it to get weight too. And so these are strain gauges. The ones we have is a little smaller than that. So these, I think I got these off of Yamaco. So some of the ratings that you have on the thing would be what you excite it with. You see that? So this guy's designed to be excited in both. And then what we got is this guy right here. This is very important. Yeah, 300 millivolts. 23 millivolts per volt. So that means the maximum this thing would put out would be what? That? No. This is my output. 3 millivolts per volt. So the maximum it would put out would be 30 millivolts.
That's 300 microvolts.
Yeah, I'm sorry, 0.3. So it would be
300 microvolts.
right. So if the maximum we'd put out, we're sighting in what? 3 millivolts. So these guys have got to be extremely accurate. I'm sorry. The instruments that measure this have to be extremely precise. So this guy here, this is more example. We used to refer to this one as a shear base. So a load cell is mounted right there. And then when you put the load out here, what's it going to cause it to do? Yeah, it's going to cause it to shift from the floor, right? And this is the example of the truck steering that we used to have. So we cite this with 10 volts too, but it's rated out to it what? 2 millivolts per volt. So this would give us up to 20 millivolts maximum for a full load. Does it give us the weight? Seems like that's what we used to buy, 500 pound, 500 pound. Calibrated springs, y'all okay there? Let's go right into these. Go right down here to Walmart and over there in their produce section. You can do, yeah. A lot of people when they buy, if you're a fisherman, they do sell digital now, but they're pretty expensive. People like to weigh their fish for some reason. Very cheap though. You can buy a calibrated spring. Now, we used to weigh the. I used to be really into paintball. We used to play paintball all the time. And when you fill up we had our own fill station, but you weigh it. That's what you do when you tell it's full. And that's the way they do if you go propane tanks or anything like that. Carbon foam, brought that in the other day. Everybody okay there? Yeah, we passed that around. So incremental encoders, absolute encoders, tach generators, AC and DC tach generators. What else did we talk about? Of course, our photoelectric sensors are our proximity sensors. We don't do a lab on a read switch. That would be a pretty easy lab. We just don't see one when we go over to the other class, right? Like I've got one. So, y'all got anything I need to look at as far as what might be on the test? You read through those discussion portions of the lab that I handed out. That's your textbook, right? I understand that. A lot of stuff.
Test is pretty much
No, it's going to cover what we've lectured. But primarily the information, but anything that comes off the discussion we're going to give y'all out another discussion thing today, right? Because most of y'all are getting through with the proximity sensors. And then the next lab we'll do is going to be liquid metal. Huh?
after the time for what?
Well, still that's proximity sensor. So it's
Oh, yeah,
not,
that's kind of fun.
yeah, so what we're doing is the first group allowed is gonna be on, we're on proximity sensors. And then the second group allowed is level, liquid level sensors. So I'll give y'all out those discussion pages today, so you'll have those to look over. And then, of course, any question from the previous test. So I'll go back, when I put y'all in lab, I'll go back and, make sure the previous test is up there. So previous test is up there? And I'll make sure I put the test with you up there too. All right, anything else? Okay, let's go to lab.